Okay, so welcome back, and this time we're going to be talking about the relationship between standard free energy and the equilibrium constant. And so when delta G is 0, we can assume that the system is going to be at equilibrium. So I'll just add that little note here. We'll assume that the situation is equilibrium. Alright, and so what that means now is that there's going to be a relationship between standard free energy and the equilibrium constant, because we're basically coming from this equation. And so when we create a situation that's considered to be equilibrium, the Q can't be Q anymore, the Q has to be K. And so we're basically just saying, alright, this is 0, so it drops out, and this side of the term comes over here, creating this. It's as if we subtracted all this information to the other side. So, just like before, anytime we're going to be using this equation, we're going to be in joules because of the R constant's relationship with joules. And we can use this equation to either solve for standard free energy if we know the value of the equilibrium constant, or we can use this as our basis, right? We can use this equation as our basis for solving for the equilibrium constant. And if we're going to do that, we're going to have to use this version of the equation to help us solve for K, where technically that's, I suppose, not down there, but up here. Standard free energy divided by negative RT. And again, it's that value of R that causes us to have standard free energy in joules. So, with that idea in mind, we've got a practice question here. What is the value of standard free energy for the reaction shown below if its equilibrium constant at 25 degrees Celsius is 3.75? So, nice thing for us is we're looking at 25 degrees Celsius. And again, if we know standard free energy for the reaction, we can adjust temperature and come up with the new K value at adjusted temperatures, which is a nice thing for us. But in this case, we have a standard temperature occurring here. So, let's take a look here. We've got delta G is going to equal, standard free energy rather, is going to equal negative RT natural log of K. So change in standard free energy is going to equal negative 8.3145 times 298, because temperature better be in Kelvin, times the natural log of 3.75. So let's see what this kicks out for us. 8.3145 times 298 times the natural log of 3.75 puts us at a value of delta G standard being, let's double check that one more time. I want to make sure I didn't miss any sort of and I did, so it's going to be negative 3274.9. And given the values we're looking at here, I'd say that this is probably going to need to adjust itself to 3 sig figs. So I'm thinking that we're looking at negative 3,270 joules. Might even be able to go down to 3,300 joules, where, because this is a constant, may not have as much of an effect on the sig figs, but it's also coming from measured numbers, so I would say 3 sig figs should be okay. Could even maybe go down to 2 sig figs based on this. So, with that being said, the other thing I want to point out is that the ending unit, based on this calculation using these numbers, is going to be in joules. So now if I wanted to, I could make an adjustment and call this negative 3.27 kilojoules would also be acceptable. That's pretty much the use for this equation. If you've got the equilibrium constant, you can get the standard free energy value. Another consideration is like this down here. What is the value of the equilibrium constant for a reaction if standard free energy is negative 234 kilojoules at 35 degrees Celsius? So now we have non-standard conditions, but we can go ahead and just use the equation that we talked about before. So we're going to use the adjusted equation. So it's basically algebraically manipulating this equation so that it solves for K instead of solving for change in standard free energy. And the way that this works is we're going to have the value E raised to the quantity delta G, right? So standard free energy divided by negative RT. Alright, so like I was saying, we've got our equation here to help us get our standard free energy turned into the equilibrium constant. And so it's time to bring in our numbers, and so K is equal to E, and this has to be negative 234,000 because when we're working with R is presented in joules, which means that our delta G value, right, our standard free energy value, also has to be represented as joules. So kilojoules converts to this many joules, right? Negative 234 kilojoules is negative 234,000 joules. That being said, we then also have a multiplied number that should be in the denominator position. So that means that I've got to have negative 8.3145 multiplied times 308 in the denominator position. So I have this extra set of parentheses to make sure that I group these two terms, because otherwise what your calculator might do is simply divide these two and then multiply that result times 308. That's not what we're looking for. That will lead to a way bigger number than we want. So as we take a look at this, we've got e to the negative 234,000 divided by parentheses negative 8.3145 times 308, end parentheses, and then final parentheses. And we get a value that's somewhere around 4.82 times 10 to the 39th. So that's a fairly large K value, which means that pretty much, we already kind of knew this with a relatively large and negative standard free energy value, that the value for the equilibrium constant was going to heavily favor the products, right? This was going to be pretty spontaneous moving towards the products side. So we've got a fairly large K, which means that the system's going to want to shift, right? Going to move towards having a lot of products in the system and not a whole lot of reactants in the system. So I hope this helps, and good luck putting it to use for yourselves.